Hello, I'm John,
And I'm Liam.
and together we are Brief.
Brief is the Biological Robotic Imaging Experimentation Framework, a multi-target, autonomous 3D modeling solution for plant and crop research.
That's Brief and what it does, but who does it help and who is it for? For my visual learners, I have two charts to demonstrate the necessity of a system like ours. Let's spot the differences. What you're looking at now is world population throughout history and its relationship to the amount of land used to create food. Can you spot the difference? Well, there isn't one. The relationship is direct, and as you can see, over the last few centuries, world population has exploded. But how does this relate to us in the 21st century? I have one more bonus chart which shows the consequences of the relationship between these trends. As you can see, this graph is representative of how the relationship between people and how we use our land has changed over the last half century. This is flipped worldwide. This may sound alarming, but this relationship has been met with an equal explosion in efficiency in how we use our land. Researchers have been able to do incredible work in revolutionizing how efficiently we grow food.
But we think the process by which scientists conduct the research could use an equally revolutionary boost in efficiency. The current state of plant research is both time-consuming and hands-on. Every day, each scientist must go into their lab, manually handle and observe each of their target plants, and record the desired data. This process is slow, manual, and subject to human error, something that is inevitable to happen. Efficient crop production requires smart solutions, and these solutions should be reached through an equally efficient process. That's where Brief comes in. Brief is a set-and-forget 3D modeling solution to the problem of tedious plant data collection. It creates accurate 3D models of multiple plant targets simultaneously and automatically through a combined robotics and algorithmic approach.
This process improves upon or corrects for several inefficiencies in current plant research. Data is collected simultaneously over a large volume of targets, making the process faster. The process is autonomous, so that researchers can focus on the data rather than its collection. And it provides a clear, precise, and holistic view of the entire life cycle of a plant in full 360 degrees. Our process is an elegant integration of consumer electronics and high-end research robotics. Here it is at a high level. At the first stage, we receive 360-degree scan data from a Microsoft Kinect, but the nature of multi-target scanning can lead to imperfections. To negate those imperfections, we use a robotic arm to reposition and rescan. This is a central focus of our team's role in the project. After the adjustment, separate scans are composited into a single flawless 3D image ready for science study. To reiterate, we use a Kinect arm to scan, a robotics arm to adjust, the process is repeated, and the image can be composited. Now that we know Brief from root to leaf, let's get a lower level view of what's under the hood.
First, we receive the Kinect scan, and if it is deemed to be insufficient, then our arm will calculate a motion plan for where it needs to go in space. This means it's going to calculate a spot where it needs to go to pick up the plant and rearrange it. In the visualization software we use, the motion plan is displayed like this. It's a very quick movement, and it's simply showing to the user what exactly is going to happen when the motion is simulated. So obviously now, the motion plan needs to be simulated. Simulation is extremely important to our project. The Shunk arm is a powerful robotic arm that has the capabilities of damaging plants on its observation table, itself, or even injuring scientists who may be within its range. This means that we need to execute every single motion plan in simulation, which will return valid if there are no collisions or if nothing wrong happened within the simulation.
Now that motion is simulated and safe, we are ready to enact the changes dictated by the motion plan using the physical arm as it did in simulation space. Here's a video of the physical arm manipulating the end effector and scan target in real space, as it did in the simulation. Finally, after the motion plan has been enacted and the plant rearranged, the targets are rescanned and hopefully enough of the image has been collected to compose a clear 3D scan. This system is made possible through the integration of several key software and hardware technologies.
Brief's main software component is ROS, the Robot Operating System. ROS is the platform on which we have developed our system, and the best thing about it is that all capabilities and functionalities that have been programmed into the robotics side can be zipped up into one modular package. From here, all the scientist needs to do is download the package from online, and then the hardware is ready to go. Next, we have MoveIt. MoveIt is the motion planning library which tells the arm how to get from one position to another. And lastly, we have RViz, which is the visualization software that shows to the scientist the motion plans that are about to be enacted in simulation.
The first of two main hardware components of the system is the Shunk lightweight arm, which offers a platform with 6 degrees of freedom for precise manipulation, as well as the capability to modularly attach first-party as well as custom end effectors. Secondly, we have integrated our own custom gripper for the end effector. It is designed to be minimally invasive and runs wirelessly using a BeagleBone Black microcontroller. All these components combine to create the Brief system for 3D modeling, a system which we are excited to demonstrate for you right now.
In this demo scenario, we have a cactus that is currently being studied by a biologist. However, the Kinect scan that just occurred was deemed insufficient. Our arm now goes into action to rearrange the cactus to a new position that will result in a successful scan. First, the visualization software displays the motion plan that is about to be simulated. Next, the motion plan is actually simulated and validated. And since these motions are valid, the physical arm then enacts them. Note that this process occurs for each of the waypoints that the arm must pass through throughout its rearrangement procedure.
The path between these waypoints are interpolated using inverse kinematics. Inverse kinematics is simply the required joint angles that are needed for the arm to be at a desired position. We chose to use a primitive box shape to represent the cactus in simulation for now, as it's easy to create in simulation and operates as a good placeholder. We also chose to model the gripper as a block on the end of the actual Shunk arm, as we do not yet have a 3D model for the custom gripper itself. Let's watch the rest of the short demo speak for itself, as the arm returns to home. Our vision for the Brief project is for it to bring us closer to a more efficient future. This includes growing food smarter, saving time, and maybe in the end, doing a little bit to save the world. Thank you for listening.